So here we are. You are on page 13. Turn to page 13 of your work packet if you're not already there. Page 13. And page 13, we are looking at this reaction. So here we see a balloon filled with a flammable gas. Now, it says here to make a sketch of that balloon and estimate its volume. Well, I think that the volume of this balloon is about 3 liters. Now that's, it could be 4. I'm pretty sure it's more than 2. We're going to call it 3 liters. And it contains hydrogen gas. So there's a conversion factor that you guys aren't familiar with yet that says if we have these conditions, we can convert from liters to moles. So that's what we're going to do here. If the pressure is 1 atmosphere and the temperature is 0, we realize that's not quite true, but we can convert that to moles because we have this conversion factor, 3 liters of hydrogen. And we're going to multiply it by this conversion factor, 22.4 liters, is 1 mole. And we want the liters to cancel out, so we're going to put it down here, 22.4 liters, 1 mole. So that will tell us, let's see, 3 divided by 22.4 is roughly 0.13, but we're going to just call it, let's call it 0.13 moles. Realize I'm breaking a few significant digit rules, but that's pretty close. So what we want to do here is find out, estimating the bond energy from your bond energy table, we want to find out how much energy will be produced when we carry out this reaction. Now, I'm going to have to go back to page 2 of your work packet. You remember you have this page that has bond energy tables. And we're just going to grab that real quick, and you are going to want to be sure you can find that because you're going to be using that in this assignment today. So we've grabbed that. Let's go put it back here on this page where we're working on this. So how much energy will this make? I mean, we can see that it releases energy, but how much will it make? So let's see if we can paste that bond energy table in here. And when we need to refer to it, it will be there. So I also want to remind you, here you see in this reaction, this is the balanced reaction. It takes 2 hydrogen molecules and 1 oxygen molecule. This equation isn't balanced. I got to put a 2 here because when we put these 2 reactants together, we're going to get 2 water molecules. So be sure you add that coefficient. You got that? Got it? Okay. So we have that 2, and you are never going to have to come up with the structural formulas on your own, but if you have them, then you can do the calculations we need to calculate. So let's draw them real quick. Hydrogen makes a single bond with another hydrogen, and there are 2 of those molecules. So if we're drawing all the reactants, we have to include both of those molecules. Oxygen forms a double bond with another oxygen, and now that is all of the reactants. let's draw all of the products. And I'm going to choose today to draw everything about the products in red. So there are two waters. That's two H2O. And in each H2O, there are two bonds that are identical in each water. Identical for our purposes here. So that is all the structural formulas of the reactants and the products. So that you have to have those as your first step. Now, a lot of times we're going to be kind of just writing them here. Like I'm going to rewrite the reactants and the products. I'm going to put the products here in red. That was the hydrogen and hydrogen. Sorry, water and water. Hydrogen in water. There we go. Those are the products. And the reactants, I'm going to put that line up here somewhere like this. The reactants were the hydrogens and the oxygen. So sometimes we might arrange them there like that in our graph. So what is the sum of the reactant bond energies? So we have two kinds of bonds. We have two of the bonds that are hydrogen attached to another hydrogen. We have two of those. So we have, actually, we're going to say we have 2 moles of those. And we're going to multiply that by the bond energy from the bond energy table. And so we're going to go over here and find that bond energy for H single bond. So you might have to search around for it for a moment. There it is. H single bond, 432 kilojoules per mole. So that's 432 kilojoules per mole. Now, I'm being careful with my units so that we see that we have the moles cancel out, and we'll just be left with kilojoules as our unit. So if you multiply that, it's going to be 864 kilojoules. That is the amount of energy you have to put in to break those hydrogen single bonds in the hydrogen molecule. You got to put that energy in. If you look closely at this image here, you'll see a candle or a piece of wood burning just below that balloon. And we have to put that energy in to get these molecules apart. It is the activation energy. Now there's one other kind of bond. We can't forget the water. We can't forget the oxygen, excuse me. We have 1 mole of these oxygen single bonds. You have 1 mole of those. And we're going to look that up on the chart here. And we have to look for the oxygen and oxygen that are involved in a single bond. And that's 494 kilojoules per mole. So let's get that. 494 kilojoules per mole. So the moles cancel out here, they factor out, and we get 494 kilojoules. So we add these together and we get 1,358. So in order to get this reaction started and to keep it going, for this 1 mole of this one reaction, we have to put in that much energy. And so we would say we increase the amount of energy of the system. So keep in mind, this is simply a system of chemicals that are residing inside that balloon. And we have to put in energy to break those bonds apart. Now, the amount of energy we put in is 1,358 kilojoules for this reaction the way it is written. That's how much energy has to go in. That amount of energy from here on our y-axis to here on our y-axis, that is the amount of energy we have to put in. It's 1,358 kilojoules. Sometimes that amount of energy is referred to as the activation energy. And what it does is it prepares all of these things to come back together. In your Pogel activity, it referred to the idea that you have Legos, but you've got to take them apart before you can rearrange them and put them back together as something else. Now, those things are sometimes listed up here. I don't usually take time to write them here, but they are here in this activation complex. Just a bunch of hydrogens and oxygens. Well, how many? There's a very specific amount, right? It's 2 oxygens and 4 hydrogens, but they're not bonded together. Now, they will bond together, and in that bonding together process, they're going to release energy. And we know from looking at our experimental results that it's going to release a lot of energy. I mean, look how much we put in. Look how much, where are they at there? Where are my pictures? We put in a little flame and we got out a large flame. It's going to put out a lot more energy than we put in. So let's calculate that. I'll quit jumping around here on the graph quite so much. Here we are back on your paper. The thing we're going to do next is we're going to find the sum of the product bond energies. The sum of the product bond energies. So the sum of the product bond energies is going to be these 4. I'm going to write it like this, 4 moles of this bond that's hydrogen to oxygen, single bond. We're going to have 4 of those. And we're going to find then that bond over here, hydrogen, oxygen. We're searching around. There it is. Now, this is the amount of energy it takes to break those apart, but of course, remember, that's just the opposite of what you get out when you put them together. So we're going to write negative 464. Negative 464 kilojoules per mole. So the amount of energy released when the products are made is going to be 4 times negative 464 kilojoules per mole, and that is negative 1,856 kilojoules. So in this reaction, we are releasing, the system releases this much energy when the bonds are formed. So when these bonds are formed and we go from this point on the graph down to this point on the graph, and we're making a bunch of new bonds, the amount of energy that the system releases is negative 1,856 kilojoules. So you can see that we've released more energy than we started with, than we put in. That's why we saw flame. Flame was flying out of this. It's an exothermic reaction. That much we know. And the reason we know that is we saw the flame that came out. And we also can tell from the change in enthalpy. What is the change in enthalpy? I'm going to go with just this black marker to calculate that. That is the amount of energy change between the reactants that were right here and the products that were right here. That is called the change in enthalpy. And if you look back at your POGL on the first page we did 2 days ago, they define this term, and I told you to be sure and notice it. Change in enthalpy. It's really just the difference between these, this increase from breaking bonds and the decrease from putting them back together again. So, all we have to do is add these two numbers together. 1,358. And this would probably be a good time to point out, you will look online and find this, and they'll say you subtract the sum of the bond energy of the reactants, that's this number right here, from the bond energy, subtract the sum of the bond energy of the products from the sum of the bond energy of the reactants. Well, that's exactly what we're doing, but we're doing it by adding these two numbers together. One of them is a negative number, and we're just adding them together, and that means we're going to go negative 1,856 kilojoules. So what is the change in enthalpy? Well, if you do that subtraction, get out my calculator, that's negative 498 kilojoules. Now, that is the amount of energy for every 2 moles of hydrogen that we started with. I think we had 2 up there. Yeah. By that I mean this 2 in the balanced chemical equation. So we could, I'm not going to take time right now, we could calculate the amount of energy involved in this ball of fire. So that's one of the useful applications of this idea. And a couple things to keep in mind. You've got to have the structural formula, and you've got to count up all the different kinds of chemical bonds. And then you have to add all of the bonds from the highlighter time. You've got to add all the bonds from the reactants, and you've got to add all the bonds from the products. And then you have to find the difference between those two numbers. If it's a negative number, the reaction is endothermic, and energy was lost from the system. Energy went flowing out in the form of light and heat. So I'm going to suggest we pause the video there for a bit. I am going to provide you some more details, but you need to go look at the other pages. You have several other pages you can work on. Page 11, page 12, page 14, I believe. I'm going to jump ahead to 14. So you should do as many of these problems as you can. It gets tricky looking at some of these, but do as many of them as you can. This, of course, is photosynthesis. You can estimate the energy captured in photosynthesis. And when I say captured, it's because the reactants are going to have energy that's lower than the products. In other words, the products of photosynthesis, glucose and other things, the product is going to contain more energy than the system had to begin with. And that energy came from the sun, and it's captured in the glucose molecule. So you have those things you can work on. I think I'm going to maybe stop the video there, and I may give you a still picture of some of the other things you might need.